thank you very much for being here and listen to my presentation. So I'm going to talk about outsourcing computations to a cloud that we don't trust, and I'm sure all of us have done this, even we have realized it or not. So this is a picture from Gothenburg, and here are some examples where we use IoT and cloud-assisted computing at the same time. So we're all aware of the Internet of Things, we're familiar with these smart watches, and I've seen, heard drones and maybe some self-driving cars, but the IoT is actually used in the smart industry, in smart buildings, in many more settings, ranging from home automation, traffic transport, payments, supply chain management, even health. So there is a constant growth of the Internet of Things. There are many predictions about how many devices we will have by 2020. The one thing is for sure that we expect a big growth. But actually, the IoT is not only these small devices that we're all familiar with and we think about when we hear the word Internet of Things, but it's also connected to the big servers, the cloud servers, that are necessary in order to store data, store information, and also perform expensive computations. Furthermore, we have all these services like medical centers, companies like health insurance companies that they need access to these data in order to provide the services they have. So it's a concept with multiple aspects, and one of the main issues we have here is that we have serious security and privacy concerns. And these security and privacy concerns, some people say, okay, security is important, privacy, do I really need to care? I need to care if we consider that there are all these legislations and regulations about privacy aspects, and the current regulation, the GDPR, we have heard about, and it's under enforcement since May 2018. Some motivation scenarios here about the importance of security. IoT is used in healthcare, so for instance this picture here shows a device that measures the insulin levels, and this can be transferred to a cloud. And there are already findings from researchers showing that all this information from health applications, 80% of health applications were examined, and often about 50% of cases the information is transferred over insecure channels. Also, I'm sure you've heard of this scandal for USA base in Afghanistan, that information was leaked through the Strava fitness application. Or when we talk about cars, cars actually are like networks on wheels, and we have this communication, car to infrastructure, and cloud computing is also involved there. There are already on the news information about cars that are being remotely hacked. So I'm sure more or less you've heard of this, and the idea was to capture your attention. But let's try to narrow down a bit the problem. So let us consider here that we have Alice. Alice is a user, is someone who has a smart watch, and she is measuring her activity levels with this smartwatch. Okay, and then we have an health insurance company here that promises to Alice to provide a health insurance package, and depending on her activity levels, if she is active enough, she will get a discount. Okay. So this is actually a paradigm that exists in some countries. So for instance, in Switzerland and in Germany, there are many health insurance companies that offer this possibility. Now Alice monitors her activity levels. She cannot store a lot of information on her smartwatch, so she needs to outsource the storage of information to an untrusted cloud server. And the health insurance company wants access to this data in order to compute functions on the data. So for instance, what is the average activity level of Alice? Okay, and let's assume that we have another party here in this setting. We call this the auditor. So maybe there is a party that wants to verify that the health insurance company provides the services that it actually promises, so that the health insurance company is fair and provides the discounts when Alice is active enough. Okay, so data are transferred from the smartwatch to the cloud server, computations are performed here, and the results are collected by the health insurance company. So what are the concerns we have? Alice has some concerns because she wants to make sure that all the information that are collected from here remain private. Okay, so all the information that are stored on the cloud, they should remain private. The cloud is not trusted. Okay. Then we have the insurance company. The insurance company wants to verify that the cloud is giving the correct computations, the correct results on the computations, and also wants to guarantee, guarantees that the data that are used for these computations are indeed coming from Alice. Okay, we want guarantees on the authenticity of the data. And we have the additional party here, the auditor, that wants to verify that the company is fair. Okay, so this is rather multidimensional. We have the data owner. The data owner generates the data through a trusted source, authenticates them, encodes the data. We have the cloud server, who is powerful, is able to perform heavy computations and store a lot of data. And these computations should not leak any information about the data X. And we have the health insurance company that says, I will give the services only if I'm convinced about the authenticity of the data, that they come from the data owner, and the correctness of the computations. Okay. And finally, we have the auditor that audits this company and wants to verify also himself this computation that's performed. So the data owner is the one that wants privacy. The cloud server is the one that is not trusted, so he should not see the data. And then the health insurance company wants integrity guarantees about the authenticity of the data, about the correctness of the computations, and the auditor is the one that wants transparency and fairness. Okay, each of these parties has its own interests. So this is a rather complicated problem. So what can we do? How can we solve this problem? A simple solution to this would be maybe to encrypt the data. If we encrypt the data, we have a good level of privacy. And maybe then we can sign the data to guarantee authenticity, that the data indeed come from the data owner. And then compute on this encrypted data. Right. What's the problem with this? Current solutions are very expensive. Usually they require both the cost of the encryption and the cost of the signatures. And this is rather a challenging problem to solve. Now, the same problem can apply also to settings where we don't have a single user. We may have multiple users and have a curator that collects data from multiple users. I don't know, maybe from the National Institute of Health. And then we may have multiple analysts, someone who is a medical researcher, someone who comes from a tobacco company, and they all want to perform computations on this data, but the data should remain private, and it should be possible to verify that what is computed by the different analysts is correct. So we are actually looking for a special feature that we call here public verification. So not only a single entity should be able to verify the correctness, but anyone should be able to verify. So this is a very active research area. There has been a lot of work on verifiable computation for a long time, right? And so I give just a sample of some solutions here, a representative sample in this area. So different solutions try to address different aspects, and the main properties that I have identified here as relevant is the security, the privacy, not leaking information about the data, the generality of the function, so what types of computations I can perform on the data, and if it's possible to verify publicly the correctness of the computations. So we have actually focused on trying to achieve all three aspects at the same time, all four aspects, sorry, at the same time: security, privacy, generality, and public verification. And we wonder, is it possible to achieve this? So what we have done is to introduce a new cryptographic primitive, homomorphic signcryption, that can be used to compute arbitrary functions on encoded data. And I'm not sure if everyone is familiar with the concept of signcryption. So signcryption means very simply that I am able to encrypt a message, so information remains confidential, and I'm also able to sign the data and have guarantees on the authenticity of the data. There has been some proposals, some instantiations on signcryption, and these instantiations are very efficient if we compare them by just encrypting and signing separately. And these, for instance, provide a 50% computation cost and 85% communication cost gain compared to just signing and encrypting. The problem with current signcryption systems is that we cannot compute with encrypted data, and we cannot verify publicly. Okay, so the question we try to address is how can we introduce a new primitive that is homomorphic signcryption and provides public verification guarantees. So we actually, the answer is affirmative. It's possible to construct this, and we introduced a new homomorphic signcryption scheme that provides public verifiability, message privacy, and can be used for arbitrary functions. And we provide the instantiations for a public evaluation when you can use a public key in order to perform the evaluation algorithm, when you can use a private key to perform the evaluation, and have two different constructions correspondingly for the two different settings. In both settings we have public verifiability and message privacy. And another aspect that we considered is it possible to incorporate this primitive in another challenging problem that we call verifiable differential privacy. And I'm going to explain more later. And just a hint, when we want to have guarantees that what I'm computing, the function I'm computing, is differential private. So, I mean, some information about this instantiation. So for the homomorphic signcryption in public evaluation, we're actually based on combining homomorphic signatures and indistinguishability obfuscation. So really heavy machinery here. So it is, the good thing is that we have proven that it's possible to construct this. The bad news is that from efficiency perspective, we're incorporating indistinguishability obfuscation, so we still need some time to have a probably practical solution. I can give you some insights on this construction. What we actually do is not that efficient because we actually perform a sequential composition. So we, in a simple words, we sign a message and then we encrypt the concatenation of the message and the signature. And in order to evaluate, we are mainly based on the evaluation function of the homomorphic signature. So given two signatures, we're able to compute a new signature that corresponds to the function of the two messages. What's the problem with that? How can we actually perform homomorphic evaluation over encrypted signatures? Because the signatures are actually encrypted, and we should be able to do that without the decryption key. In order to address this, we use some magic coming from indistinguishability obfuscation. So what we do is that the decryption key is embedded on an obfuscated program, and this program has some special functionality. So you are able to, this functionality is that the program is able to decrypt the signcryption, recover the signatures, and compute on the new signature that is derived from the two initial signatures. And using the public verification of the homomorphic signature, anyone can verify that indeed Y is the result of the computation and sigma is the corresponding signature.
So the IO is used to also extract Y?
IO is used to extract Y, yes.
What, to compute Y?
To compute Y, we use actually, yes, at the end the program is able to do this. We incorporate this computation in the obfuscated program.
Okay.
But, and also for the private evaluation setting, here the evaluation is a bit different. In the public, we have a private key. Here we have in the public we have a public key. Here we have a private key. Of course, we rely on functional encryption and homomorphic signatures. So the positive thing is that we have a positive answer that it's possible to build this primitive. However, regarding efficiency, since we don't currently have any good efficient instantiations for obfuscation and for functional encryption, maybe we need to wait a bit on advance on that, although there were some good contributions recently. So what do we gain with this approach? We have privacy guarantees, and we're able to guarantee authenticity of the data. And since before we were not able to compute on signcrypted data, and we were not able to verify publicly, and we overcome these two constraints we had. So if we try to compare our approach with existing approaches, we have message privacy, and additionally the Y that is actually computed at the end do not leak any information about the initial messages. A verification anyone can perform, and the computations are possible on encoded data. All right. Another aspect, so some highlights now I'm giving you in this area that we have worked on, that we considered is, all right, this sounds quite good, so you have strong privacy guarantees just by encrypting everything. Is there any other information leakage? And differential privacy is a very nice framework that gives us the possibility to find out information about a population of users without leaking any sensitive information about individuals. So what we wonder is it possible to achieve this concept that we call verifiable differential privacy? So not only have guarantees that indeed the computation is correct, but also have guarantees that the function that is used is differentially private. And this is even more challenging problem, I would say, because in order to achieve that, you have three constraints. The first is to guarantee the correctness of the computation. The second is to guarantee that the randomness, the noise that is incorporated in order to perform the computation of the differentially private function is coming from a pure source of randomness. And the third is to have guarantees that indeed the sensitivity of the function is good, is actually differentially private. So by incorporating this primitive of homomorphic signature, we can capture the first one, that indeed we have verifiable computation. We can also use a simple zero-knowledge protocol in order to have some guarantees on the source of the randomness. So this is an illustration of a very simple zero-knowledge protocol to do that. But the third remains of how to achieve, to have guarantees that the sensitivity of the function is really good. There is some work on this, but it's still something that we need to explore. Some other work that is very relevant to this topic we have worked on is what about considering when we have joint computations. So when we actually consider that we may have data from different sources. So in this example, I have three databases, and we want these different clients to perform a joint computation of a function f over a series of joint inputs. So let's say x1, x2, x3 comes from the different sources, and then we want to compute f of x1, x2, x3. The same setting can apply also in other application scenarios, such as smart grids. The special restriction we pose here is that the client are not able to interact with each other, and they need to rely on external, one or more external cloud servers. Oops. Yes, so we actually introduced a new cryptographic primitive, multi-key homomorphic authenticators, so have different cases for homomorphic signatures and homomorphic marks. Each client signs her data with her own key. The cloud is able to compute and produce a signature for the result, and we're able to check the validity of the computed result by verifying just the signature. So
does this depend on the how does the function that the cloud computes goes into this structure?
How does the function?
Yeah, the function that the cloud computes, right? How does it fit in a way?
What do you mean? How does it fit in? The cloud computes the function, and the input comes from the different sources.
Yeah.
What is the problem? You mean if it's a general function, if it can compute any type of functions? Is this your question?
How does the signature appear on the result then?
Each of these sources sign their data, they submit the information on the cloud, and the cloud is able to perform a computation on the data and the signature, and you're able to verify the correctness of the computation using the signature.
That I follow, but the original people, I mean the signature they put on X1, let's say, is it tailored for the F that you're computing?
No, it is not tailored for a specific function. No, so, but this is, I don't have more details here. but it's a very interesting work. Maybe we can discuss further if you want. Now, another highlight I want to present on that.
I think it's in a sense fully homomorphic signature scheme, so which allows one to compute any signature.
Yes, it's fully, yes. Was this your question?
Yeah.
Oh, sorry, I didn't realize. So, the security without the secret key, a malicious cloud cannot actually convince for false results. This is a rather very interesting aspect of the solution. The only limitation we have here is how this signature grows if you have multiple users. So it grows actually linearly with the number of users. Another problem we consider, because I got often this feedback, all right, this sounds really interesting, but you know, this does not work in practice, and this is not a practical solution. Can we do something that will be used in practice? So we explored another way to achieve something similar that is based on homomorphic secret sharing. And homomorphic actually secret sharing was initially proposed by Boyle et al. And it actually says that we have multiple clients, and each of these clients split their input to multiple servers. Okay, so each server has multiple shares for each client, and then each server is able to perform a partial evaluation of a function, and if we combine all these evaluations, we're able to build the final computation of the function for the different inputs. Okay, so this was the result that was proposed by Boyle et al. We found this very interesting and said, okay, this is also very relevant for outsourcing computations. And just to illustrate an example here, let's say that we have some households, and each of these households has some share, x1, x2, x3, etc. And they all split their inputs to different servers. By doing that, each of these servers is able to perform some computations, partial evaluation of the function y1, y2, y3, y4, and by doing a multiplication here, we can get the final result y. Okay, so this is something that is allowed with homomorphic secret sharing. And this is a specific example for the multiplicative setting. So what we wondered was, how about having some guarantees that the actual computation here, y, is correct? How can we verify the correctness of the computation? And what we introduced was the concept of verifiable homomorphic secret sharing, where here we have again the partial evaluation of the function by different servers, but also, except of the final computation f, we have also a proof that verifies that the final output is indeed correct. So in order to define this verifiable homomorphic secret sharing, we have these different algorithms sharing the secrets by the clients. The partial evaluation and the partial proof is performed by the servers, and we're able to perform the final evaluation. Actually, this can be performed by anyone, because these values y1, y2, ym are public. So we have also again the feature of public verification. Okay, and this is a recent result. We have improved this here. So I give you here a concrete construction on how to do that. It's based on bilinear maps, so it's rather heavy, but for the server side it doesn't seem to be that heavy. So not only we're able to perform the computation of the function y, but also a proof sigma that is also a multiplication of the different proofs that are generated by each server. Okay, this gives an idea about the construction. Right, I think that was mainly my talk, and also we provide guarantees about the correctness, the security, and the verifiability. So if I want to conclude, I can say that IoT technologies provide many advantages, but also raise serious security and privacy concerns. It's not possible anymore to allow this deploy now and fix later model, and we need a new paradigm shift, different architectures, solutions that are open and can be audited, and support from legislation and economic incentives are always an advantage for this problem. Of course, homomorphic computations seem to be the answer to this, but we still need further advances in order to reach a practical level. We can achieve a good security and privacy level for simple computations, and maybe adopting decentralized solutions could be a good solution. Thank you very much for your attention.
Have you implemented any of these? Well, the function secret sharing thing is kind of vaguely implementable, yeah?
It's very easy to implement. We have not implemented it yet. We plan to implement it for an extension of the paper, yes. The others, no.
Okay, let's thank the speaker again.